Chapter 13, Solutions. It's going to take some stuff that you already know, think of it in a different light. Now, there is a little bit of math in this chapter, so we're back to it. So, stay on board with us here. Now, I realize that because I've been there, I know how this works. I know that sometimes you can sit here and as I go through this math, you can follow me. But then when you do it on your own, not so much. Okay? But realize the point of lecture is to at least put it in your head one time where you have been able to follow it so that you know you're capable of following it. It should be a morale booster for you. Okay? You know that you're capable of following it. Now it's a matter of how do I put this in my head based upon my experiences, based upon what I know I'm good at, what I'm not good at, how I learn things, how can I put this in my head? Now, obviously, I as an instructor can't go around and do that for you because I would love to be able to. I'd love to have a class with one student, and then we just spend the whole entire semester learning the way you want to learn. But that's not the way life's going to work. So we'll do our best, okay? As a little opener here, probably don't know this place, but if you do, you knew more than I did before I read through this. There's a little place called, right in the elbow of Africa, a little place called Cameroon. It's got a lake in it right here at this, about where this little point is. Okay, it's right in Central Africa. In 1986, on the date that's listed up there, there was a geological event that happened. This place sits on a very weak tectonic area where there's a lot of activity, volcanic types of activity, not giant, mountainous, I don't know if that's the word or not, volcanoes, but just underground magma activity where vents can leak out and things can come up to the surface and that kind of stuff. What happened in this area, they weren't for sure at first what caused this, but there was an accident that happened that involved a burping of a lake called Lake Nyos. It's right, like I said, it's right in here. It's right on top of a little volcanic area. And it sort of bubbled and it burped. And when it burped, what they ultimately realized, although it was too late by the time they found out, was that a large carbon dioxide cloud had escaped from this gas, from the water. And when it came up, carbon dioxide is actually heavier than air. So what happens is, if you ever watch CSI on CSI Miami, where the one, I've talked about this before, the subliming CO2 block hangs down by, when it comes out, the CO2 hangs down the bottom of the floor and that kind of thing. CO2 is more dense and it's a little bit heavier than air. So what happened is, there was a village that was in the valley right below this lake. And when it burped up that carbon dioxide, you couldn't see it, but it just sort of flowed over the side and went down into the valley, and it asphyxiated, it choked and suffocated a lot of the inhabitants in that area, as well as the animals and the livestock and that kind of stuff. So here's some totals on that. I've got a link if you want to read more about it. You can click on that. There's just a one-page little summary of what happened. But there is, from underground, okay, there's a lot of material. There's organic material that can get mixed in with all of this, and CO2 is a natural byproduct of volcanic activity. When a volcano erupts, it shoots up a lot of carbon dioxide and sulfur dioxide up in the air. And that's where we get some natural forms of acid rain. CO2 reacts with H2O. Carbon dioxide and water vapor make carbonic acid, which can give the rain a little bit of an acidic characteristic. And sulfur dioxide can actually react with water to form, what do you think? If SO2 reacts with H2O, what do you think might form? Sulfuric acid. That's exactly right. So there's another component of acid rain. Okay, just so happens that with industrial revolution and that kind of stuff, a lot of coal burning. We still burn a lot of coal in our culture. We're moving towards cleaner energy sources, nuclear power, hydrogen power, that kind of stuff. But for right now, we rely a lot on fossil fuels, especially coal. And the burning of coal and the emissions of coal byproducts, one of those things is SO2. There's a lot of sulfur dioxide. If you watch commercials, you can sort of, they hint at what's called clean coal. Clean coal is coal that has been tried to remove a lot of the sulfur content out of it so that it doesn't get put up into the air and form these kinds of things. I'll talk about acid rain in the next chapter. It causes a lot more problems than what you realize. People just think, oh, acid rain, I've heard of that, who cares? I don't melt when it rains, so it doesn't matter to me. But there's a lot of impact that it has biologically, historically, structurally on components, and we'll talk about that later. But CO2 is not necessarily toxic in itself because it's all around us, but what does happen is it goes down and it displaces the air you would normally breathe, kicks out oxygen and other things, and as a result, when you take that in, you basically starve yourself of oxygen. You can't get that oxygen in, so that's asphyxiation. So anyway, that's what happened. They're trying to figure out how to prevent that from happening again. And what they've done now is obviously hindsight's 2020, but they've actually got sort of agitators in there now. Because what happened was, we know now, based upon the pressure unit that we've studied, is that as water is stacked on top of itself, it increases in pressure, right? The deeper down you go, the more pressure there is. So what happens is normally carbon dioxide can be suspended and made into a solution. We'll talk about that definition in a minute. But carbon dioxide can be sort of trapped between water molecules. It is like in Coke whenever it's pressurized before you pop that top. Okay? It's pressurized, it's mixed in with the water molecules, and it's held there. And if you have a high pressure system, it's holding that gas in, which is sort of like what we have here. All that gas is escaping from the bottom, from the Earth's crust, and up through. And then that standing body of water sort of holds it down and keeps it in the solution. But there comes a point when if enough gas accumulates, that it can overcome the amount of pressure that's coming down upon it, and those things do not stay dissolved in that water anymore, and instead they escape to the surface. And once a few of them start to escape to the surface, it's a feed-forward reaction because it starts to alleviate more and more pressure, and it starts to spread things out, and more can start coming up and follow, and before long, you get an entire sort of little eruption of CO2. A bubbling to the surface and a burp. Okay. So one of the ways around this is to vent it at the bottom. You can put vents in that go all the way down so that any pressure buildup of CO2 can sort of slowly leak out as it forms and goes up to the atmosphere. Or you can agitate it, pump it, shift it around just to keep those molecules loose and keep them from building up and stacking up on one another when they get to the bottom. These are a couple solutions that were implemented. You see the word supersaturation here. I'm going to come back to this in a minute. But you know what it means to be saturated, right? You think about like your clothes are saturated with sweat. What that would technically mean is that it's holding as much as it possibly can. In chemistry, we have a state that we call supersaturation that we can't achieve. If we manipulate pressure, we manipulate temperature, we can create supersaturated solutions, solutions that are forced to hold more inside of them than what they normally would. This would be an example of that. With tremendous pressure from the standing water in this lake, you were able to supersaturate that solution. So the second the pressure changes were allowed, then it would escape. Okay. All right, so this brings us to the definition of solution. That lake water was an example of solution. It was a good example of not only what a solution is, but how you can affect a solution, and how gas and liquid together can both be a solution. When you think of solutions, you typically think of two things mixed together. Like a lot of your favorite, for those of you who partake in these sort of extracurricular activities, a lot of your favorite beverages may be solutions of two different or more different types of things. Those are solutions. You're mixing liquids together. But, you could actually have a solution of two solids mixed together. What? Anybody know? What's an example of a solid solution? Now, a solution will appear to be, like, as you well know, we've done enough in lab now to see that when I set out a bunch of different types of solutions, a lot of things just look like water. And they're not. So don't drink them, right? It appears to be one substance, so really there's a lot of stuff in there. It could be several things dissolved in it, okay? So most of the homogeneous materials that we see are actually called solutions. The air and the lake water that we've talked about, that's a solution. So by definition, it's got to have two things. It's going to have what's called a solute. You guys probably already know this, right? And a solvent. The solute is that which is dissolved. So in salt water, what's your solute? Salt. It tends to disappear when you put it in your solvent. The solvent is the thing that does the dissolving. It works on the thing that you're trying to dissolve. So water would be the solvent. Generally, the solvent doesn't change its state. So if you're a gas, if you're using a gas as a solvent, whenever you mix things together, you're still going to get a gas. Okay? If you mix things together and your solvent is a liquid, then it's going to be in liquid form whenever you mix everything together. So typically that doesn't change. Also, the solvent is generally that which is in the larger amount present. Like if you're dissolving salt in water, you're not going to use more salt than you are water. You're going to use more water than you have salt. So typically that's going to be the case. Solvent's going to be in higher proportion. Okay, and this too, we've already talked about this, but this last bullet, aqueous solutions. We know what that means now. That means you've got something dissolved in water. We symbolize that with AQ in chemistry. That's an aqueous solution. All right, here's some examples of brass. You don't have to know these, but brass is a solution. It's a solution of copper and zinc. And depending on how much of each is present, you get different compounds with different names, different situations with different names. Okay, if you're just using it for decoration, it's going to be mostly copper and much less zinc. Zinc is going to be more structurally sound. It's going to be a harder material. The more zinc it has, the more copper it has, the softer it's going to be. So you can see the difference in some of these things. All right. Now, as far as types of solutions, we know that there's what's called gaseous solutions, liquid solutions, solid solutions. We already know this. I've mentioned it. But if you're going to have a gaseous solution, really the only thing you're going to be able to put together in terms of solute and solvent are two gases. Okay? If you take a gas solute and a gas solvent, you can generally make a solution out of that. Not really gas and liquid, not really gas and solid. But as far as liquid solutions go, you can have a gas as your solute and a liquid as your solvent, such as the lake that we just talked about, the pop that you drink. That's carbonated beverages, right? Carbonated means it's pumped in carbon dioxide and pressurized to hold that in. Liquid and liquid, that's an easy one. You take a liquid and dissolve it in something else. Solid and liquid, you could take solid salt, dissolve it in a liquid, then now you've got a solution. So you get more flexibility with liquid solution. With solid solutions, you're going to have solid and solid, like brass. You're going to have to mix together zinc and copper. All right. Now, I don't know if this word, amalgams, is a word that is sort of used in the English vocabulary to mean something outside of chemistry. It sort of means a mixture of things together. But I don't know if you've heard that word or not, but in its true sense, it's in reference to the element mercury. What do we know about mercury? What makes it unique?
Liquid at room temperature.
There you go. That's the big one. It's a metal. It's the only metal that is liquid at room temperature. But it still retains almost the density of metals. So I mean it's pretty dense, but it's still a liquid at room temperature. So solutions that contain mercury and some other metal are called amalgams. This is nice in terms of metallurgy, which is chemistry associated with metals, okay? Because you can make solutions with mercury and something else because mercury is a liquid, so it's easy to put things into it. You'll find this a lot, like in dental fillings. A lot of that is like a mercury and silver amalgam. Sometimes mercury and tin amalgams. Amalgams can be used as well. So anyway, that's any solution, though, that's just specific to mercury. That's why I throw this out there. But in generic form, any solution that contains metal and a metal solvent, in other words, two metals stuck together, two or more metals stuck together to make some type of solution, we call that an alloy. It could be solid, liquid, doesn't matter. So an alloy is any time there's two or more types of metal ions present that are making up this solution. Okay, we know this as well. Whenever you can dissolve something in something else, it's said to be soluble, right? And so thus insoluble would be the opposite. You drop it in there, nothing happens. This is stuff we learned from that one lab already. I've already mentioned this rule as well, so this should be review. But the chemist's rule of thumb in terms of dissolving is what? Like dissolves like. Someone care to explain how that works? Why is it that like dissolves like? Why can I use water to clean up most things, but I can't use water to clean up, let's say, grease from the kitchen? One person, give me, I don't want everybody talking at once this time. Oh, you got to give me more than that. Those are just catchwords. I need to know how that works. Okay, why aren't they attracted to those other molecules? You're right. Because what? Who does? That's right. Water. Okay. Right. The water molecules are very polar. The fats and greases are very nonpolar, so as a result, water molecules want to attract to something polar. So if there's nothing there to attract that's polar, they're going to attract to themselves, and they're going to pull together, and they're going to kick everything else out of the way, and the other stuff's going to float on top of them. Okay, usually, unless something's more dense and push the water out of the way. Most of the time, the water will. All right, so if you have a situation like sodium and chloride, obviously those are made of ions. So we actually have charges. We've surpassed polarity now. We've got into actual separate charges, real charges. So as a result, water can interact. The negative part, the partial negative of oxygen can attract to sodium. The partial positive of hydrogen can stick to chlorine or chloride ions and pull them apart. But if you put in something else that didn't have charges or didn't have polarity of its molecule, then the water would have nothing to interact with. So we would assume then, why can we use, let's use what we just said, why then can I use, let's say, kerosene or gasoline to clean off a tar type of substance better than water? Because why? Okay, you're right. But my question is why? Why will kerosene work? That's what it will do. But I want to know why. Yeah. The bottom line is, and it's all going to the same place. Okay? Everyone's feeding in, so you're not wrong. The bottom line is, if you put something that's nonpolar in with something else that's nonpolar, you can assume that both of those are very weakly attracted, right? So as a result, when you mix them together, they're probably just as attracted to the other things as they are themselves. So that means, unlike water that's going to stick to itself, these guys are just going to stay spread out and react with whoever's around them. Does that make sense? Okay. So that's why like dissolves like. Okay, so there's a lot of solvents that we use. We have alcohol is not quite as polar as water. Water is definitely more polar. Alcohol can be used sometimes whenever water doesn't work. You know, sometimes like some of the permanent markers and that kind of stuff you can take off with alcohol, but not with water, even though alcohol is still polar. But it's just not as polar as water, so it doesn't stick together as well as water does to itself. Acetone is even less polar than that. I have acetone bottles in the chemistry lab for that reason. If something doesn't get cleaned with water, then try acetone. Then you get into actually good nonpolar solvents. Benzene, these things are much more dangerous. You can't pour these things down the drain, that kind of stuff. Benzene, hexane, diethyl ether, we've mentioned that before. Methylethyl ketone, MEK, for anybody who works in a factory or anything like that. These are all common nonpolar substances. They tend to smell like the paint thinner kind of stuff. That's what these kind of things are down here. Which is, paint thinner, mineral spirits, that kind of stuff. Those are typically nonpolar type substances. Why they're used instead of water and soaps and detergents. Okay, so we know this already. Ions are obviously going to dissolve in water. Polar molecules can dissolve in water. We know that nonpolar molecules will not be able to dissolve in water. Now, from a biological perspective, this is important because I don't know if any of you ever have to take any advanced human physiology or anything like that, but one of the things you would learn about, because I teach that as well, and one of the things we just finished talking about was the different, vitamins, those are chemicals. And some vitamins are water soluble, some vitamins are fat soluble. So it's, some of your vitamins and minerals and things that you need, vitamins, not minerals. Some of the vitamins that you need are going to be able to get in your blood plasma, stay dissolved, and travel around and get dumped off where they need to go. Others, you have to have cholesterol present, you have to have fat cells present, you have to have lipids in your bloodstream in order to grab onto those other guys. They won't dissolve in water, so they have to get something that's non-polar to stick to, take them into your cells and that kind of stuff. So all fat isn't bad, all cholesterol isn't bad. It has an important chemical role in the body. All right. Now, there are many molecules, especially the bigger molecules we get. If you get into organic chemistry, you can get some big molecules out there. Take a look at this one. Beta-carotene, C40H56. Pretty big molecule. Now, some molecules have both polar and nonpolar structures, depending on the area of the molecule that you're in. There could be a polar region over here. There could be an area where there's nonpolar. That's the way soap works, right? I said that one end of it is polar, and one end of it is a tail that's nonpolar. A head that's nonpolar and a tail that is polar, so that the head can bind with something that's nonpolar, and then that negatively charged or polar tail sticking out the back can stick with water and help break it down. Water can pull it apart then. But many molecules have both polar and nonpolar structures. It gets more complicated in that case. So whether or not they're going to dissolve in water depends on a lot of geography type of situations. How many polar spots are there? Where is it located? How are they bent? How is it positioned? That kind of stuff. So, all right, and then this is a visualization of the dissolution process when things dissolve. We've already talked about this as well. But if you are dissolving salt, realize how it works. Each of these ions are going to get surrounded, and because the partial positive parts of water will be sort of gravitated towards the chloride ions, and the same thing will happen to the other side of the water with sodium, and it'll pull it all apart. So all those atoms are still there. They look like they've disappeared, but they haven't. They're there. You can get them back out. How would I get all this salt back out? What could I do? Evaporate all the water away, and then I'm left with these guys are going. I can supply enough energy to where these guys actually escape, and chloride and sodium ions I haven't supplied enough energy to them to reach their boiling point. The rest of these guys the water molecules will go away, leave me behind just those two atoms, and I've got solid salt again. So that's called solvation. Okay, whenever the solvent acts on the solute and pulls it apart, that's just a name given to it is solvation. Okay, another words that we've probably already ran across, miscible and immiscible. Okay, now technically, when we did this before, I think we've run across this in lab already, haven't we, or not? When I mentioned it before, I just talked about whether or not it dissolves, and then it's going to be miscible. If it dissolves, then it's immiscible if it doesn't. Well, at the time, that's all I wanted to say, but there's a more specifically correct definition of that. Okay, it's about mutual solubility. If two things are together, and not only that means I could use either one as the solvent or either one as the solute, and it doesn't matter which way I look at it, either way I get it dissolved. If that can happen in that case, that's what miscibility is. So, for example, alcohol and water. Whether I take a little bit of alcohol and add it to water and stir it around, or I take a little bit of water and add it to alcohol and stir it around, realize the result is the same in terms of its ability to go into solution. Okay? So that means alcohol and water are miscible. Either of those can act as a solute or a solvent in either case. Right, yes. Oil and water are immiscible. It doesn't matter how much you have. It doesn't matter which one you try to use as the solute or the solvent. They're not going together. Okay? So that would be immiscible. All right. Now we have another word called solubility. That is the degree to which you can get something to dissolve. So the solubility of something is how much of it can I put in there and get it to dissolve, like in water, for example. The maximum amount of solute that I can put in a given amount of solute and get it all to look like it disappeared. Okay? All right. This comes into play. Anybody make rock candy or like that hard Christmas candy or whatever? Yeah. You're doing chemistry whether you realize it or not. Okay, we're going to take a look at this. All right, there's 3 different states of solubility. If something has been dissolved in something, there's 3 different degrees of solubility. Okay, we've got what's called a saturated solution. We've already talked about this. That means the solution is holding as much as it possibly can under normal conditions. Then we've got unsaturated. That means you've added a pinch, you've got a lot more to go. You can keep adding more. You have not saturated that solution yet. It's got more holding capacity than what you've used. Then we've got what's called supersaturated solutions. I've already mentioned this. By altering pressure, temperature, that kind of thing, we know that we can supersaturate solutions under certain circumstances. Okay? They're holding more than they should be able to. Now, as a result, these are often unstable. A little bump, for example, on a lake, if you could bump a lake. If there was a lake here or a big bowl of water that was really deep and it had a buildup of gas on the bottom and it hadn't escaped yet, and I just bumped it a little bit to shift that, then it's very unstable. It would erupt. It would release its gas. There's also some, and it made me think of an article I read not too long ago. There are methane pockets that have been found in the oceans, in some of the seas, that is a result of like some of this tectonic activity and that kind of stuff. And they're talking about what would the implications be if any of these pockets ever got loose and it came to the surface and erupted. Would it cause an explosion? Would it ignite? Given the friction, given the heat, given the pressure, what kind of impact would that have on the ocean ecosystem? These are big. I'm not talking about like the size of this classroom big. I'm talking miles and miles and miles and miles, square miles of methane pockets that are underneath the ocean. This could have huge impact. How would it affect the atmosphere? All that kind of stuff. So it's pretty interesting stuff. It's like we sit here and we don't think about it. And all these potential things could go wrong in a fraction of a second and just take out everything. Ask the dinosaurs. Go ahead. Maybe. I don't know. I can't remember because I just watched a show about that the other day, and I can't remember what they were talking about because I was distracted. But I'm not sure. I'm not sure what they're suggesting there. I've heard everything from crazy conspiracy theories to but as far as the most credible argument, I'm not sure. But it very well could be. I mean, if that's true, I mean, if you alter density, and you can change the density of the underlying, it's affecting the buoyant force of something, then you could change whether or not something floats or sinks. So, I mean, I don't know. It's interesting, though. Find out and then bring in some stuff and let me know. I'm interested in stuff. Now, why I talk about rock candy. This would be sort of a unsaturated versus saturated versus supersaturated type of condition. If you take something that's supersaturated, which is what you would do if you take boiling water and you get it really, really hot and you dissolve sugar in it, you're going to dissolve a lot more than what you normally could in normal circumstances. And then part of the making of the rock candy and the hard candy kind of stuff is a cooling process where like you could take a string, say you want to put it on a string and you didn't want to just make the pieces. You would take this really hot sugar water and you could add flavoring or whatever, food coloring, whatever you want to do. But then as it's cooling, you leave a string in there or you leave a stick in there or something like that. Because what happens is at a very high temperature, you've increased this energy, you've caused and allowed the sugar to dissolve at a much higher proportion than what normally would occur. And as this cools, here's what you witness. As it cools and molecules settle down and some of that energy has already evaporated and left and went away, it starts to recrystallize is what happens. The stuff that was already supersaturated and was held in solution, when the temperature drops, it is no longer held in solution. So anything past what would normally dissolve now goes out. It's called precipitates out in the solution. And if you give a little string or a stick on there, it gives it a surface for it to adhere to. And when it does, it'll recrystallize around, for structural purposes, it'll crystallize around some kind of base that you put in there for it to grab onto. And that's sort of the basis of that. You intentionally supersaturate that solution and then crystallize it out. Now, that is a purification process. It's used in chemistry, in laboratory chemistry, as well as in your kitchen, because what you actually have done is taking, if there was any impurities in that sugar, if it wasn't pure sugar, then what you have effectively done is by supersaturating it, separated all of its components out, and when you recrystallize, what happens is that only the sugar molecules themselves, a higher percentage of just pure sugar molecules, are what recrystallize. And anything that was contaminated or anything that was impure, not necessarily bad, but just part of the process that was locked up in those sugar, can now actually gets pushed out and is out in the solution now. And the actual crystals that you get are more pure than what you had to begin with. So, all right, I don't need to go through this. We've already discussed this enough. So. We've heard this word before as well. Electrolyte, electrolytic solution. What does that mean? It means that you have ions that are dissolved in water that have the ability to transmit electricity. Okay? Electrolyte solutions are like this. Salt water is a good electrolyte solution. If you're sitting in, I don't know if you'd want to try this or not, but if you're sitting in a giant tub of distilled water, pure H2O with nothing else in it, is a very, very weak electrical conductor, to the point where you throw that appliance in, you can sit there and nothing should happen. Well, at least nothing bad. Now, the reason you don't want to fill up your bathtub out of the tap water and do the same thing is because tap water contains a lot of dissolved ions, irons, magnesium, calcium, carbonates, a lot of other things. And we know how ions work now. We know how electrons work. When two atoms come up to each other or two molecules come up, when there's a chemical reaction, electrons are transferred or shared or anything like that. You get a movement of electrons. And guess what a movement of electrons is? Electricity. Okay? So when you get things that are passing electrons back and forth, you're creating an electrical current when that happens. So the more positive and negative charged ions that you have in a solution, the more electrolytic that solution will be. Okay? Now, you think about electrolytes in the body, of course, sodium, calcium, potassium, chloride ions, that kind of stuff. You think about Gatorade. Replenish your electrolytes. You can't just put in pure water into your body. That would be a bad idea. Because the way the body works is you excrete a lot of salts. You excrete, through sweat, through the urinary system, through exhalation, things like that. You're excreting things besides water that you need to put back. Because if you do not put them back, you're going to screw up where the water moves in your body. I'll show you how at the end. If you never understood this whole osmosis thing, I'm going to discuss at the end of this chapter and show you how important it is to maintain not only proper water balance, but proper salt balance in your body as well, and the implications that can have. Okay, now, if you have something called a strong electrolyte, what that means is you have something like this, something that when you put it in solution, it completely dissociates and all of its parts fall apart, and those parts are charged. They can conduct electricity like you have here. Salt water is a very good electrolyte. Okay, then you have non-electrolytes. If you tried to set in a big tub of pure water that had sugar dissolved in it, you would also not get shocked because sugar is a terrible electrolyte. Why? Because the molecules, when you dissolve sugar, they don't separate out into ions. They stay in their molecular form. They stay in, like, for example, if it was glucose, C6H12O6, it just stays all lumped together. There's no polarity. There's no ionic movement. You just got these molecules floating around in there. So that's a terrible electrolyte. A weak electrolyte, so we've got strong, non, and then weak. Weak is something that when you put it in there, it's halfway in between these two. Some of them, we haven't talked about acids, weak acids and strong acids yet, have we? But anyways, sometimes when you stick things into solution, you may, if you could freeze time and look at it, you may see that all of the parts are dissolved like you would have in a strong electrolyte, like in salt. Sodium's over here, chloride's over here, they're all spread out. In a weak electrolyte, not everything dissociates. You may have 30% of these salt molecules that have dissociated, while the remaining 70% are still intact, and they're still stuck together. Some molecules can do that. If you do that, and you witness that, you've got a weak electrolyte solution instead of a strong one, because there's not as many ions available to conduct electricity. We know this too. If you want to dissolve something, anybody have hummingbird feeders set out? Okay. How do you make the sugar water? Do you just dump some sugar in the water? No, you got to heat the crap out of it. You got to stir it, and you heat it up. It dissolves a lot better. You can get more sugar in there, right? Sugar doesn't dissolve very well at all anyway. You put it in coffee, it'll dissolve pretty good. You put it in Kool-Aid, doesn't dissolve all that easily. Okay? You can stir it, but heat is the key. You could actually, if you heat it up, it's going to dissolve a lot faster. And we know that to be true on a lot of things. So here's just a visual representation of that. Now, as for salt, you can see that salt itself doesn't make much of a difference when you start cranking up the heat because it's pretty soluble. Other things that makes a huge difference, like calcium chloride. Calcium chloride dissolves in water, but not very well. If you crank up the heat, it spikes up. It makes it really easy, about anywhere from 20 to 30 degrees Celsius, above room, a little bit above room temperature. Then we can get it to dissolve pretty easily. Okay, so the higher the temperature, the higher the solubility of that solid in a liquid is going to be. The lower the temp, the opposite is going to be true. So now, my wife, she'll deny it. Okay, but she not that she won't deny this part, but she likes to drink hot pop. Okay, she doesn't like cold pop. Well, she likes it fine, but she prefers warmer pop. And the reason is because of the, what do you know about warm pop compared to cold pop if you drink it? It's a lot fizzier. Okay, why is that the case? Go ahead if you want to answer. It has to do with how well things are dissolved, but what I want to point out is when you're dissolving a solid in a liquid, high temperature is a good thing because you're trying to make both things a liquid. But when you're dissolving a gas in a liquid, do you think you want high temperature? What do you think high temperature will cause to happen? Yeah, the gas will want to absorb that energy and escape even more. So there's a middle ground. What you want is, if you want to take a solid and dissolve it in a liquid, you want to heat it up a lot till you get to both of whether a liquid. If you've got a gas in a liquid, you want to cool it down so that that gas doesn't escape that liquid. Okay? Either cool it down or pressurize it, but we're talking about temperature now, so cool it down. So it says warm pop fizzes much more than cold pop because CO2 solubility decreases as temperature increases. Okay? Why does pop explode if you put it in the freezer? Well, it's water-based, right? So it's expanding literally. The water can crystallize, and it can. Now, if you put it in just 0 degrees Celsius, it probably wouldn't work. I'm going to explain that in this chapter, because when you start adding stuff to water, it changes the freezing point and changes the boiling point. It'll lower the freezing point, have to make it colder to freeze, and it can make it hotter to boil. But in typical freezers that are, say, minus 4 degrees Celsius, you've gone far enough to where you can still freeze things that are dissolved in water, okay, the water itself. That she likes it better because of this effect. That she I don't know why. I don't know why she just can't say because she likes it to tickle her nose or whatever she drinks it. But it sounds too dumb, so she'll deny it. But anyways, so there's the case for that. Now this has, again, biological. I'm coming from that kind of background. So the biological implications here are water and oxygen. The fish that need oxygen and aquatic creatures that need oxygen to live, you think, and this is a mistake that a lot of people make too, right? You think you want to keep your fish nice and warm. You don't want to leave them outside in that cold water. Realize that oxygen dissolves better in cold water than it does warm water. So if you bring them in and try to cozy them up to about 85, 90 degrees in their fish tank, you're going to kill them. And the reason you're going to kill them is because you're going to starve them of oxygen. The oxygen will not stay dissolved in solutions that warm. I suck at raising. I cannot keep fish, man. They always die. I don't know why. It's just the curse that I have. Okay, we also know this, that if I've got gas molecules mixed in with a liquid, I take it and I press down on it like in a pop can and I seal it, I know that the pressure can hold this in. Okay, so the more pressure I have, the more soluble this is going to be. And that's why whenever you pop that top on your can, you alleviate that pressure. Now that pressure can become in equilibrium with the external environment. All that comes flying out, okay? And it's not, a lot of your carbon dioxide starts to escape, and it will continue to escape until you reach what's called flat, right? The pop goes flat. That means that it's lost the carbon dioxide, it's escaped. So you can't just open it and leave it set there, okay? Now, why then? I want to mention this because I see people do this all the time, okay? Tapping the can. Now think about this, folks. Use a little logic. You do it because someone told you to do it, because your mom did it, whoever, right? I'm not saying it's a bad idea. I'm just saying think it through. You take a can, you shake it up. So you supply kinetic energy, frictional energy. The molecules get excited, they start expanding more, and the pressure inside of the can starts to increase, right? Now, naturally, most of the pressure is going to build at the top. That's why it all is foamy, right? Because gas rises, it's less dense, it's going to collect at the top of the can. So if you hold it out and you pop the top, then obviously a bunch of stuff's going to come flying out. Now, if you tap the top of the can, I want to know how this is going to help you. Down. Oh, you're tapping it down. Are you? Are you physically coming in contact with these CO2 bubbles to force them back down in solution? Does it? Well, that really wouldn't matter because you've not reduced the amount of CO2 that's going to escape. Maybe it's leaking through. Okay, why? You're buying time is what you're doing. That's what you're doing. You're buying time. You tap on this can, and what you're doing is allowing some of the energy from those molecules to dissipate, pass through the can, warm up just a little bit to get passed on to the surroundings. And the whole time you're thinking, I'm doing this. Right? You're buying time. Now, I'm not saying it doesn't work at all, because in theory it would help a little bit, because here's what's going to happen. The stuff that's going to make an eruption and the stuff that's going to spew forth the soda as it comes out of the can are not going to be all those ones that are trapped at the top. Because when you pop the top, the ones on the top escape, and they're not pushing anything out of the way, except maybe just a little bit of vapor, and a little bit of pop and whatever. The ones you care about are these ones down here that are stuck to the side. Because pressure has increased in the can, they start to collect, and like little gas areas start to collect on the interior. Like if it was a clear can, you could probably see it. Like if you had a clear bottle of pop and you shake it up, you can see where those bubbles start to collect on the side. Those are the bubbles you worry about, because the second you break that, they're all shooting to the top. And when they all shoot to the top, guess what they're bringing with them? Everything that's in the way, all that pop. So, my point to all of this is if you're going to be a can tapper, great. Tap the side. That's exactly right. Tap the side. Tap the side. And then you tap those bubbles and knock them loose, and they'll go to the top, and then they won't spew out as much soda at the top whenever you open it, or beer, or whatever it is you're drinking. Because you know, the next time you're sitting at the bar, you're thinking, and you know, you're good and loaded at this point, and you're sitting there, you're trying to impress everybody around. You're sitting there tapping on this can, looking around. That's right. You know, so I don't know. All right. These are things people need to know. Okay. All right. Now, dilutions. Okay. See, these are things that are just swept under the rug. It's just those things that happen. The chemistry of life, and how to get through everyday life, the whole tire situation, and how to tap cans and all that. You know how much work that would be to come up with that class? Whew. All right. All right. Dilution. We know what dilution means from a practical sense. We know that we do it all the time. If you use bleach, if you use any kind of cleaning, you know that you dilute things because you want to make them less concentrated. You want to make them not as strong. Now, the difference between... Do what? What we want to do now, though, is look at this from what's called a quantitative aspect. We are going to know what dilutions are, but then we're going to put some math into it to calculate the degree of dilution. That's what chemistry is going to be about. This is one of the most important laboratory skills that you learn. Now, in biology, like if you do MLT or other things like that where you're doing solutions in class, it's more going to be like parts or like serial dilutions, like 1/10 or whatever. You guys all right? Well, this is a little bit different because this is actually a step past that. The chemistry dilutions are going to be more in terms of focusing on the solute that is dissolved. Tell me how much solute is present in a given amount of solution. And that becomes very important. Think of medicine. You think of your dosage levels, right? If you're supposed to take 500 milligrams per your body weight, you don't want somebody giving you twice that much because the concentration is going to be twice as much. So you can see in all aspects of science why it's important to be able to calculate these dilutions and be able to use them, especially in chemistry. All right, so dilute solutions have low solute concentrations. The stuff that is dissolved in the solvent is very low, so it's dilute. And then on the flip side, these concentrated solutions have a whole lot of solute in that solution. Okay. Here's what we need to know. To describe a solution, this is the whole point of this, is now we know what a solution is, we know the different types and that kind of stuff. Now, how can we most efficiently and thoroughly describe a solution that you have in front of you? If you've ever looked at any of this stuff in lab, I might have said like, or had a label on something that said the number 2 with a big M and then HCl, like 2 molar hydrochloric acid. What does that mean? 0.50 molar potassium iodide. What does that mean? Because if I give you a bottle of 0.001 molar hydrochloric acid and I give you a bottle of 10 molar hydrochloric acid, you need to know the difference, because if you don't, you're going to learn very quickly. Okay? Yeah, one's going to digest some flesh, and the other one's just probably not. You're not even going to feel. Okay? It's a matter of concentration. It's a matter of describing the solutions that we have. Okay? All right. So we need to know the components, what's in it, hydrochloric acid, and the relative amounts. How much of it is in this given amount of solution? Okay? So this is where concentration comes in. The amount of solute in a given amount of solution. I'm going to skip this check mark in a minute because I'm going to talk about it later. Okay? So how much solute is in a given amount of solution? For example, if I have 1 liter of something, how many moles of solute are dissolved in that 1 liter? That's what that big M stands for on those solutions that I write in lab. It's called molarity. It's moles per liter. If I had 1 liter of this substance, and I say that it's 2 molar, if I have 2 big M, that means I've got 2 moles of whatever it is that's in there, potassium iodide, let's say. I would have, if I had 1 liter of this solution, you'll be able to count 2 moles of it present, 2 moles of potassium iodide present. So it tells you how much of the solute is in a given amount of solution. Okay, one way to do it is mass percent. From the biological perspective, this you might come into this as well. For example, Ringer solution or a saline drip. It's 0.9% sodium chloride. It's salt water. It's less than 1% salt water. So parts of solute in every 100 parts of solution is mass percent. Percent means of 100. So if something is 9%, it's 9 of 100. Okay, 9 parts out of a possible 100. So if a solution is 0.9% by mass, that means there are 0.9 grams of solute in every 100 grams of the total solution. That does not mean 0.9 grams of solute per 100 grams of solvent. Think about that. That's 2 different things. That's saying that I took 100 grams of water, 0.9 grams of salt, and mixed them together, then I have 100.9 grams. Right? That's not what I'm saying here. I'm saying the total mass, after everything is mixed together, is 100 grams. So in this case, I would have 0.9 grams of salt and 99.1 grams of water. That's what that is saying. Okay? So 0.9, is that right? Did I do that right? Okay. 0.9 grams of solute for every 100 grams of solution. That's mass percent. Okay? This is wrong. This should be 9 kilograms of solvent in every 100 kilograms of solution. That's simple math. I'm not sure how I missed that one. Hey, she didn't type those. Thank you very much. I don't need this crap. All right. So the masses are additive. That means you can take these masses together. You know that grams is grams. Okay. Now, if we have 1 mole, it may weigh different of 2 different things, but a gram is a gram. Across the board. So the mass of the solution, then, if I want to take the mass of the solution, like I said a minute ago, it's actually the sum of the masses of the solute and the solvent. In other words, 100 grams of solution means I've taken, in this case, 0.9 grams of salt, 99.1 grams of water. I can add those gram values together to get the total mass of the solution. That's what this is saying. Okay, so that's mass percent. Just like free throw percentage is the part divided by the whole, what you got, the whole theoretical yield thing. We talked about what you got, what you're supposed to get, all that. The mass of the solute, just the solute part itself, divided by all of it added together. The whole thing, the solution. That's how you get percentage. mass percent. All right, so let's look at an example of calculating mass percent. Calculate the mass percent of a solution containing 27.5 grams of ethanol, which is ethyl alcohol, and 175 milliliters of water. Assume the density of water is 1 gram per milliliter. Now notice what I've done here. Think about what you're doing. If you want mass percent, you want the grams of solute divided by the grams of the total solution. Do you have grams of solute? Yes, 27.5 grams. Do you have grams of total solution? Can you get it? How? Conversion, what do you mean? Yes. If I have 175 milliliters of water, and I know that for every milliliter of water I have, it weighs 1 gram, guess how many grams of water I have? 175 grams. So I would take that number divided by what? That divided by 175? This is my solute. This is my solvent. I got to put them together to get the solution. So I would take 27.5 divided by 27.5 plus 175 grams. Okay? And then that will be my answer. Okay? Well, yeah. Well, no, I mean, like if you get 0.98 as your answer, you know that that's 98%. I mean, if you have to write that out, then that's fine. So, long way about it. Realize that I'm going to need, I've got the mass of the solute, and I've got the volume of the solvent. I need the mass of the solvent, and I can use density to find that. Once I have those two things, I can calculate mass percent. That's what this is saying. So if you look at the numbers, 175 milliliters. We did this in our head, but here will be the way you write it out. You know that if the density of water is 1 gram per milliliter, that means if you have a milliliter of it, it's going to weigh a gram. So if you have 175 milliliters, it's obviously going to weigh 175 grams. There's your solvent. All right, now to get my total solution, I've got to take my solute, which is this, add it to my solvent, which is this, and now I've got 202.5, keeping track of my sig figs, for my total mass of my solution. So now all I got to do is take 27.5 divided by my total mass of solution. I've got the mass percent of this solution. So 13.58, 13.6%. It's 13.6% ethanol. So what would that be? That would be 7 no. Let's round up 14. That would be like 7 proof. Proof is twice the, no wait, other way around. That would be 26, right? Yeah, 26 proof or whatever. Proof is twice the percentage of the alcohol content. So, you know, but yeah, that's what why don't I just teach distillation and everything while I'm at it? Oh, you cut me deep. What you got to do that for? Jeez, I don't do nothing to you. All right. All right, now, we know this to be true. If you know something is 12% by mass, then you know that 12 grams of the solute is present in 100 grams of the total solution. That's what it tells you. All right, so if that's true, guess what you have? A conversion factor. Yeah, more of them. That's right. 12 grams of sugar, if we had a 12% sugar solution, that means there would be 12 grams of sugar equivalent to or present in a total of 100 grams of solution. That means we can use that in our math. Okay? Let me show you what I mean. Using mass percent in calculations. Let's use this as a conversion factor. A soft drink contains 11.5% sucrose, table sugar, by mass. What volume of soft drink in milliliters contains 85.2 grams of sucrose? Assume the density is 1 gram per milliliter. Now think about what you're doing. You need two things to answer this question. If you're going to, anytime we're dealing with a percent by mass, we know that we're talking about mass of solute divided by mass of total solution. So let's look at how this applies. We have the answer, we have the percent by mass answer right here as 11.5%. Okay? So in decimal form, 0.115, if we were going to use it to set it equal to something. All right, I want to know what volume of soft drink in milliliters contains 85.2 grams of sucrose. So in other words, if this is going to be my solute, right, dissolved, I've got my answer in terms of what it's going to be equal to. When I take mass of solute divided by mass of solution, my answer should be 0.115, right? If that's the case, I've got my numerator here. I'm looking for my denominator. I've got to solve for grams of total solution. Now, this asks for a volume. Realize that if you know the density of something, you can go back and forth between the grams of it and the amount present of it in terms of volume. Okay? Do that very easily. So if you think about this in this respect, what you should get is realize that, okay, we know that mass of solute divided by mass of solution equals percent by mass, right? I have mass of solute, 85.2 grams. Do I have mass of solution? No, I do not. Do I have what it's equal to? Yes. So rearrange algebraically and solve for the mass of the total solution. If I find the mass of the total solution, I know that however many grams I have, that's how many milliliters I have, right? So then I can just, if I calculate 355 grams, then that's 355 milliliters if I know the density is 1. Okay? All right, so this would be an example of, like, if you were trying to answer, you know, as far as a life kind of thing, say you had to keep track of how much of something you ate every day. And now, you could follow a chart, whether it's sodium or carbs or whatever. You could follow a chart that tells you how many points this is worth or how many points this is worth, because that's really easy to do. Or you could not waste all that money, and you could sit down and figure it out yourself. You could figure out, okay, this has this many grams. It's listed on your food. It's got this many grams of carbs, or this many calories from fat, or this much sugar. Okay? If it's got this much sugar in it, how much of these things can I eat and stay within my daily allowance that I'm supposed to have for carbs or whatever? That's all those tables are that you look at every day. Someone's already done that math, and you've paid them for doing that math. Now, you be the people that do it yourself now instead of paying somebody else to do it. That's the whole point of getting an education. Okay? Not that you have to do that. It's a overarching kind of general idea that I'm trying to get across. Okay, get people to pay you for what you know. Stop paying other people. Okay. All right. So here's what we're going to do. We are going to use this, figure out how many grams of solution I need to equal, when I set those together as a fraction, to equal 0.115. And then I'm going to figure out, then that's going to give me how many grams of solution I have. I'm going to convert that to milliliters, and I know how many of this stuff I can drink. Okay. All right, a little problem solving is all it is. Now this is what I'm saying. You can't just memorize steps here. You got to think about what you're doing, and you got to think about how am I going to get to point A to point B. You've got to understand the problem. That's why chemistry is different than just math. You look at a problem in a book, you can memorize steps how to solve it. Everybody hates story problems. Story problems are problem solving. That's the real world. That is, the real world doesn't come up and say, hey, for today, solve this math problem. And it's all spelled out for you. That's not the way it works. Okay, you've got to apply it to real conditions. So we can go through all of this, or you can let that confuse you. Think about what I just said. That's the key. Okay, we've already talked about how we're going to solve this. So what do? I take my 85.2 grams of sucrose. I realize that I have, according to this, 11.5% of a sucrose solution. What that means is that if I had 100 grams of solution, I would have 11.5 grams of sucrose present. This ratio is maintained according to this percentage. All right? So that means I can use it to go from grams of sucrose to grams of solution. It's a conversion factor. So set it up. Take that times 100 divided by 11.5. Now I've combined the steps here. If you want to stop here, you can. Let's stop here for a second. Let's do this step and then stop. What's your answer going to be in? Grams of solution, right? Now once you have an answer in grams of solution, how do you go from grams of solution to milliliters of solution? You use your density, Where's it at? Your density has a conversion factor. It's 1 to 1. Okay? Every 1 gram for every 1 milliliter. Now, in your head, you can just do this and not even do the math. If you know it's 1 to 1, then this fraction is not even necessary out here. You've already got your answer. Just change the units. However, when you get into things that are like 1.21 grams per milliliter, then you got to set this up. Okay? So what you get is 740.87 milliliters. Round up, 741. Just to give you an idea, there's about 355 milliliters in a can of pop. Okay, so this is, what is that? More than 2 cans of pop, a little bit more than 2 cans of pop to get 85.2 grams. Now think about that. Think about, you've weighed enough grams on a scale now to know what 85, get a general idea as to what 85 grams represents. That's a lot of sugar. Okay, think of that big weigh boat. You got to fill that big weigh boat up to get, anywhere close to 85.2 grams. Your beakers weigh like 120 grams. Your 250 milliliter beaker, something like that. So I mean, this is a lot of sugar. You get things like Mountain Dew and some of that stuff that's high sugar, some of that cheap pop especially, like if you go to Aldi, yeah, it's cheap. Don't get me wrong, it's a good buy, but it's a ton more sugar and a ton more carbs than what normal pop would be as well. Take a look at those labels if you don't believe me. So your couple cans of pop, you're cranking out a lot of sugar. So people make fun of me for drinking that Pepsi One stuff, but there's just Splenda in there. There's no actual sugar. So. All right. Let's see if we can end on one more. I will. Okay, I'm going to end on this slide. Okay, let me finish this one. Now, what we're getting ready to start talking about is some things that you would do if you were working in a lab and preparing solutions. It's very important that you understand the theory behind this. When I have a solution that we have to use for lab, I don't have like all the possible concentrations of solutions sitting around everywhere. I keep stock solutions. And I look at the lab and decide, okay, what strength do we need to use for this lab based upon the reaction at hand? How am I going to mix it up? If I'm going to keep in my acid cabinet 12 molar hydrochloric acid, I don't want people coming in contact with that, but I want to make 1 molar to use for our lab. How do I obviously going to dilute it, right? I'm going to take some out and dilute it, but I got to know how much, because I got to be able to keep track of how much I am diluting it and how am I going to get to a certain value that is safe and that I want to use. So we're going to talk about preparing solutions. You need to know amount of solution and concentration of solution. You need to know how much of it do I need and how strong do I want it to be. That's a simple question. Okay? How much of it do I need? How strong do I want it to be? Okay, so you want to calculate the mass of the solute that you need. Okay, so you figure out if you're going to make a solution, I need this many grams of salt. Then I'm going to dissolve it. Okay, how much water am I going to put in? Because if I only put 250 milliliters of water and dissolve it in 250 milliliters, that's going to be more concentrated than if I put it in 1 liter of water and dissolve it. So I've got to have a ratio. I've got to keep track of the math there. All right, so I can use my concentration as a conversion factor. For example, if I want to create a 5% solution, 5% by mass, if I want a 5% sodium chloride solution, how do I make it? Not just how do you calculate it, how do you physically make this solution? That means for every 100 grams of solution that is present, if it's 5%, that means I'm going to need 5 grams of solute. So for a 5% solution of sodium chloride, I want my total solution. I would decide how many grams I want. If I wanted 200 grams, 200 milliliters, that's the density of water is 1, right? So I can do that in my head. So if I want 250 milliliters, let's keep it simple, 200. If I want 200 milliliters of water, or of total solution, I mean, I'm going to need 200 grams total solution, right? Since I'm dealing with water and the density is 1. So how many grams of solute would I need if I wanted 200 grams of solution? I would need 10, right? So that's what I'm talking about. You got to keep track. You got to maintain that concentration. So in this case, if I only want 100 milliliters of solution and I'm doing water as my solvent, then I want 100 grams to be my final total. I know that I'm going to need 5 grams of solute in that total. Okay? Now, without looking, how do you think I'm going to make this solution? What can I do? Say I'm going to use sodium chloride. I want a 5% sodium chloride solution by mass, and I want 100 grams of it, or in other words, 100 milliliters of it. How would I make it? Do you think that the actual perfect numbers for the density of salt and the density of water are the same? No, they're not. So they don't actually take up the same amount of space. That's the answer I expected, so that's fine. That's what most people do. And most of the time you can get away with that. But there's a better way to do it. What's the proper way to do it, you think? It's easier than that. Oh, it's easier than that. It's easy. Well, then you're going overboard, right? So, in our case, before I get to this problem, realize, here's what we can do. We can put our container that we're going to hold the solution in on a balance, right? Pair the balance. We're at 0. We put in 5 grams of salt. Then we pour in water until it weighs 100 grams. It's that simple. Right? Don't make it harder than it needs to be. Okay? That's how you'd make a 5% solution. You know that your total weight has to be 100 grams. Put it on there, tare it, put in your 5 grams of solute, add water until the weight's 100 grams. Okay? Same thing here. You look over this one. I want to know how to prepare 250 grams of a 5% glucose solution. It's the same concept, but it's not as easy in terms of 5 grams per 100. I want 5 grams per 100, but I've got 250 now. So how would you do that, Matt? How many grams of solute would you need? For every 100, you would need 5. You would need 12.5 grams, right? So you do the same thing. Put 12.5 grams of sugar in, pour in water until it reaches 250 grams on your scale. Okay? That's the easy one. We'll do the hard one next. I've got your tests up here if you want to see those. If not,